on. So we're gonna find out how to match an antenna to a feed line and phasing lines when you have arrays or stacked antennas. And one they threw in previous question pool about a Wilkinson divider. Nobody knew what that was. Like I said before, the main reason to match, well, I guess there's two reasons. To match your antenna to your feed line impedance is to get the maximum power to the antenna and also not burn out the power transistors in your transmitter. It wasn't as big a problem with tube type transmitters. They would tolerate much higher SWRs, but the solid state ones don't like really high SWR coming back. And that's why most of them are designed so they start cutting power back when they detect a high enough SWR or reflected power coming back. Uh, so the mismatch, if it's something other than 50 and you're feeding it with 50, you get what's called a reflection. And they have a term called reflection coefficient, which mathematically they represent with the tau signal, one of those Greek letters. And it's the ratio of the reflected over the forward voltage. And it's used in the actual SWR calculation, where it's 1 plus the reflection coefficient divided by 1 minus. And you do that ratio and you come up with the SWR. It's approximately the same thing as if you say you had a 100 ohm antenna and you're feeding with 50, you just do that ratio and you have an SWR of 2. You come out with about the same answer. This is just more mathematical. So what parameter describes the interaction of a load and transmission line? Wow. Bravo. Okay. Matches. There's one called a hairpin match because it resembles kind of a hairpin. I guess we used to call them bobby pins. Do they still call them bobby pins? Uh, Normally you'd see it on a Yagi where they'll normally have some impedance down in the 20, 25, maybe 30 ohm range. So it's fairly low impedance. And they'll use what's called a hairpin match to do it. And this is one of the cases where the driven element has to be isolated in order to do this. And what you do is calculate the length of this little loop so that it adds enough reactance onto the antenna to correct it back up to 50 ohms. And this is kind of what it looks like. You're just feeding the driven element like a normal dipole. And you add this little hairpin loop, which you kind of have to do a calculator to figure out how wide it has to be and how long it has to be in order to give you basically what we call a conjugate match. So it counteracts whatever the reactance is on the antenna. You give it the opposite reactance to cancel them out. So all you have is the real part. So what Yagi-driven element feed point impedance is required to use a beta or hairpin matching system? Beta is just another name for it. The driven element must be capacitive. Oh, when matching, which matching system for Yagis requires the driven element to be insulated from the boom? Gamma match. It's called that because it sort of resembles the Greek gamma symbol. And you can match an unbalanced feed line to the antenna. It's a little more complicated than the others, where it has a series capacitor adjustable and an adjustable shunt so that you can match the capacitive reactance and the impedance point where you actually make the connection. They use it on things like Yagis to directly connect a tower, where you use the actual tower itself as an antenna, which could be grounded. I mean, it's kind of this amazing stuff where, because you're attaching it to part of the tower at two different points at RF, those are not zero. There's impedance between the two. So that's how it actually works. Here's a picture one where they're doing it on a 2-meter Yagi. And you have this sliding called shorting bar. It's kind of like, if you think of the hairpin, except here we can make it adjustable by where that short is. And then this other part of it is tubular with the kind of like the inside of coax in it. So it makes it an adjustable capacitor. So you can adjust both of those things. You can adjust the capacitance and you can adjust the where the impedance tap is to match very closely. I haven't actually tried to tune one, but I understand they work quite well. It's just kind of fiddly.
They do. The reason they make actually, you take the inside of a coax, like you said, and actually put it into a tube, and then make the adjustments, the lengths and everything to get it resonant. And it's easy to connect your cable to connect it right up to a SO239
Right.
typical. So in that VHF, UHF range.
And this one, the element can be connected to the boom, doesn't have to be isolated, and it doesn't have to be split. It can be a continuous element. What antenna matching system matches coaxial cable to an antenna by connecting the shield to the center of the antenna and the conductor a fraction of the wavelength to one side? Well, only because we just talked about it.
I know.
But that long description there is confusing.
Yeah, that is.
What is the purpose of a series capacitor in a gamma match? Well, we can limit A and C, right?
So Cancel. Problem.
Well, let's see. I don't remember.
I don't know.
You're going to cancel out the inductive reactance that you're going to have in that loop that you added. Which of the following is used to shunt feed a grounded tower at its base?
I just wanted to be A.
Yeah, we won't get to A. I don't even know what that is.
Disappointing.
Although I've heard of the bazooka, and a double bazooka, but I don't know what a bazooka match is. A stub match, somewhat similar to the hairpin, except we use a piece of transmission line, and we have it either open or shorted. So it allows you to add whatever reactance you need depending on its length to compensate for the antenna to make the match. So here's a couple examples where you have your normal transmission line coming in and it's connected to your antenna where you have some load, which is the real part or the ohmic resistance and the radiation resistance plus whatever the reactance is. So ideally, X would be 0 if it was at resonant. And you add a stub of transmission line at a specific distance from the connection point, and you make it a certain length, and it's either open or shorted, depending on which way you're trying to go. If it's open here, it means it's a low impedance on this end, and vice versa. If it's shorted here, it's a high impedance on this end. So the fact that it's not going to be necessarily quarter wavelength long, it will be somewhere in between 0 and infinity. And that's that distance, that length determines what the impedance is going to be and what the reactance is going to be. What matching system uses a short length of transmission line connected in parallel with the feed line at or near the feed point?
Well, it's almost simple because it's going in order, right? So it would be D. But if it was all mixed up, then I would probably have.
But we didn't talk about T-match.
Well, I know, but what I mean is when I on the test, I'm really gonna have to focus on what each of these do.
There's no guarantee that on the test the answer's in the same order.
Right.
Unless it's all the above, which will always be D. But they can be mixed up.
Yeah.
Since it said all the above, it was A.
Huh?
He said, yeah, since it's all of it where.
Okay, a quarter wave transformer. Oh, and that last one, the sub match. That's where you can either find an online calculator or you can use a Smith chart, which we'll talk about later. The quarter wave transformer allows you to match things like a 100 ohm feed point to a 50 ohm, where you just, like I mentioned earlier, you take a 1/4 inch length of 75 ohm and connect it between your 50 ohm and your 100 ohm antenna, and it will give you a match, almost perfect. That's another one that you can optimize on the Smith chart and get it even closer. But we're not going to learn how to do that. We're just going to talk about some very basics of the Smith chart. And the formula that you use for the quarter wave transformer is you multiply the two impedances that you want to match and take the square root of it, which is kind of giving you the median. And that's the impedance that you need for that 1/4 inch line. And it turns out, and they always use that example, 150. Well, it turns out that the answer is 75, so it works. If you had some different numbers, you might not be able to find a piece of transmission line that's the right impedance. So your choices are going to be, well, 50's out because you already have that. So you could do 75 or 300 or 450 or 600 with the ladder lines. If it's not one of those, then you can't really do it as a quarter wave transformer.
Bob,
Yes.
we've covered a lot of different matching methods, but do any of these increase the bandwidth of an antenna? Or I should say, what is the relationship between bandwidth and at a particular frequency and a match?
Well, the only way it could affect the bandwidth is if it affects the Q, and I don't think it would, because all you're doing is matching the impedance of the antenna to your feed line. So it
has no effect.
It shouldn't have any effect on the Q of the antenna.
Okay, thank you.
Because when it's matched, the antenna hasn't changed, it's whatever it was. What you're seeing should be purely resistive. In the real world, it won't be exactly, but in theory, it would be resistive if it was at resonance. So which of these transmission line impedances would be suitable for constructing a quarter wave Q section for matching a 100 ohm feed point to a 50 ohm transmission line? That's a hard one.
Yeah, that's good.
I'll get this one.
You didn't have to do the math either.
Did it in my
Another use to use coaxial cable, choosing where you care about the length, is for a phasing line. So we talked about the vertical arrays, where you're going to feed one of them at 90 degrees or one of them at 180 degrees. You do that with a phasing line. So you actually use a length of coax that's for whatever frequency you want, gives you that amount of phase shift. So you feed one directly, and then you feed one through a longer piece of coax in order to get the 90 or 180 degree phase shift. So what's the purpose of using multiple driven elements connected through phasing lines? Alpha?
Mhm.
And a Wilkinson divider. I'd never heard of this before it came up on the question pool either. But they apparently use them for microwave, where it's really just a 50 ohm splitter. It's maybe a little bit different than the cheap ones you used to buy for your TV, 75 ohm splitters, where this one maintains 50 ohm on the input and 50 ohms on the two outputs. And it's just a bunch of, you can see in the box, there's a terminating resistor and those two coils. Looks like it's fairly simple. I guess they just wanted to throw a question in about something different. You may never ever see one.
Is this new this time?
I don't know. I know when it first came up, some of the guys that had been doing this for a long time didn't know what it was. So I don't think it's that common. And like I said, it's microwave, so most, hams don't play with microwave. So what's the use for a Wilkinson divider? Charlie, sound good.